Good afternoon and welcome everyone to this webinar on compressed air, optimising efficiency and new smart alternatives. We have a 1 hour presentation for you this afternoon and 3 excellent speakers. So I hope you have some really good questions ready for them. My name is Jared Leake and I'm the CEO for the Australian Alliance for Energy Productivity. And I'd like to begin this webinar with an acknowledgement of country. And on behalf of all the people here at A2EP and on this webinar, I'd like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea and community, and we pay our respects to their elders. And for those of you that are new to A2EP, we are a member-funded industry association, and we have a wonderful array of members that share our vision to decarbonise in a smart and fast way using energy productivity. And we certainly welcome more members, and the bigger the network, the better the sharing of innovation and advice, and the faster we can see decarbonisation. Just a little bit of housekeeping for you all today. So these slides will be sent out to you in the coming days, along with a recording. We certainly intend to have questions at the very end of the 3 presentations. But if you have some questions you'd like answered before that, put them in the Q&A. And after each speaker is finished, they're likely to be able to get back to you and answer those questions. If not, feel free to have a little comments in the sidebar on the chat there. Carry on a discussion there if you like. But we'll hope to make this really nice and interactive for you today. So our speakers today, we have Michael East from Green Energy and Carbon Management, Edwin Burwood from Energy and Carbon Solutions, and Alan Pearce from RMIT. We're going to start today with Michael from Green Energy and Carbon Management. And so with Michael's going to help us set the scene here and understand some of the bigger picture and bigger issues when it comes to compressed air. This is, as always, it's not just a straight out technical one-for-one easy type drop in. There's so many different things to consider, and there's certain steps to go through that. And so it's great that we have Michael here today. Michael has a background of 16 years in energy consulting, and so which is great, so that he does know a lot about energy retailing and understanding of wholesale prices and what have you, wholesale markets, as well as a really good understanding of compressed air, refrigeration and boiler systems. So with that, Michael, I'll ask you to share your screen and over to you to take us through the high-level issues and strategies and how we start thinking and looking at compressed air.
Great, thank you, Jared. Have you got the screen share there?
Well, I shall stop sharing and that might help with you. Go for it. That's come up, all yours.
Perfect, excellent, thank you. All right, so thanks for the introduction, Jared, on myself. I'll also give you guys just a quick note on who Green Energy and Carbon Management are. We're a relatively new business in our 2nd year of operation, but we do have a wealth of experience with over 40 years combined in the energy space, and we focus largely on industrial manufacturing, but also some other large complex energy users, such as universities. So we help out with carbon strategies, roadmaps, energy monitoring, energy audits in general, but also technology-specific audits and opportunities. Hence today's topic on compressed air. So as you pointed out, Jared, I'm focusing more on not so much the technical issues, but the bigger perspective on how and why you might be focusing on compressed air. And what we've seen from those businesses that do a really good job of actually reducing their compressed air consumption and costs. So we've seen the best results can be achieved where companies implement a compressed air strategic management plan. So that doesn't need to be, a long complex document. Doesn't even have to be in a written form. But it does require that you sit down and think about, okay, what's my specific objective that I'm trying to achieve? And that might be something like, we want to supply compressed air efficiently as possible with the existing assets. Maybe you want to reduce compressed air consumption to avoid capital expenditure and upsizing the compressor. Or maybe you've got corporate targets that are energy or cost or carbon per ton of product, and you want to minimize the compressed air contribution towards that. Having that objective in place and following a continuous improvement approach can help you take that compressed air system from the old reactive, look, it's adequately sized. We've got budgeted maintenance costs there, and when we replace it, yeah, we'll come to that at some point. But flip that to a more proactive approach to be able to say, look, we've got an integrated system. It's optimized in terms of the supply, distribution, and demand sections. And it's got a known performance and known succession planning. So straight away, you're on the front foot, and you can, that you're going to be able to take control of that energy and cost. The approach that GECM takes has strong synergies with ISO 50001 for energy management systems, and that's effectively what we can see in this graphic here. We've highlighted the 4 key components to a compressed air system that need to be considered in order to really manage that and optimize the performance, both in terms of output and input in terms of energy. And within each quadrant here, you can see, some of the examples of efficiency measures or activities that you might want to have a look at or address in order to make some progress. But the reality is it comes down to making sure all 4 of these are working in conjunction with each other. So for example, the common obvious project is make sure you've got a VSD controlled compressor, but that's not going to be any good to you if you've got piping restrictions in your distribution network, which means, maybe you've got multiple compressor rooms, and those compressor houses can't see each other clearly through the pressure and the piping restrictions. So you've got control conflicts and excess energy being used. And that might also mean your supply pressure is higher than it needs to be, meaning all your demand side applications are using a lot more air than what they realistically need to. But as they say, ignorance is bliss. So I don't know how many compressed air systems I've seen where there's 0 metering, but as soon as you start to get the metering in there, you get a lot more visibility and transparency on what's actually happening, rather than just taking a short snapshot in time for a couple of days or a week, or just maintenance personnel eyeballing the compressors to see how they're operating. And it really is a key component to that continuous improvement cycle, or as some of you might know it, the plan, do, check, adjust. And really, like it's in the title, right? Check. You can't check anything unless you've got some sort of metering and monitoring in place. And to be fair, you can't do proper planning either unless you've got that information on what the system's doing, and an idea of what you want to do to improve it. So here we've just got a basic schematic of a compressed air system, and some basic metering. So there's a power meter on each compressor, and then we've got a flow, pressure, and temperature sensor on the outlet of the compressor house, so the supply side. And now there's many different ways that you can do the metering. Some people like to have flow per compressor, but for energy management, I've found that 80–90% of the applications, it's more than suitable to have a metering configuration like this one. And it really comes down to what your objective is as well. But something that's, I think, overlooked with metering systems and applications to compressed air is what value does that actually add to each layer of a business. If you've got metering in place, your maintenance teams can start to question, okay, service techs came in last week and did a service of the machines. Did they change set points? So we're still operating our control logic and maintaining our efficiency. That metering gives you transparency over that. It also lets the maintenance teams keep track of what the leak loss rate is on the site, and whether it's actually worthwhile going around and chasing and fixing those leaks. It also lets your engineering team make proactive, informed decisions about the compressor, dryer, piping, and air receiver sizing. and then have certainty around the business case when they put that up for, CapEx or, modifications, and getting away from that reactive approach of, well, let's just do a like for like replacement because we've run out of time, but let's make sure it's got a VSD on it. So you can make better decisions with plenty of time up your sleeve. Then when we start to get to the sustainability and environment managers, having that metering in place is essential to being able to unlock what are the opportunities available that are unique to this site and this compressed air system. There's always the generic ones, but when you come in and say, right, you need to fix leaks, you need to reduce system pressure, it's very generic and you get little traction, you get little results. Having a look at a system and saying, right, what does this plant need, and what can we do to make this as efficient and as streamlined as possible, without being unnecessarily tight. You really need to have that metered data to understand it. It also lets the sustainability teams make sure that any changes and energy savings that have been seen are retained over time. So there's nothing worse than coming back 6, 12, 24 months later and going, hang on a minute, our efficiency has gone back up by 40%. Why is that? If you've got the metering in place, you would have known the day that occurred, and you've got a chance of being able to quickly pinpoint it. This type of metering also then fits in conjunction with metering the rest of your energy consuming systems, and rolling up into senior management reports. The best plant manager I've seen, each month has his sheet of KPIs color coded, can quickly skim down the list and go, right, compressed air, specific energy consumption, KPIs green, all good. Hang on a minute, my consumption here for cumulative cubic meters for the month is in the red. Why is that? We're up 35% compared to last month. So straight away he knows, right, there's something on the demand side of the system, and that needs further investigation to go and hunt down. But without, that hasn't been left for 6 or 12 months, people can get on it straight away and be proactive. Which means if you've got senior management with publicly stated energy or carbon claims, or reporting to the board against specific KPIs, the metering just rolls up and lets you facilitate a clear understanding of what you're doing. So as Jared, you alluded to at the start, there's many technical things that you can do with compressed air, and people do often get caught up in those technical components. But where we've seen the best success is where people have addressed the softer aspects around process, KPIs, and people. And I've summarized what I think are the best areas to look at here. So I've already mentioned having a compressed air objective in place, but it's important that that's in the form of something that's like a smart KPI that probably many of you are familiar with. This ensures that what you're actually trying to achieve is possible, it's practical. It puts a timeline around it so that you make sure there's some focus and ideally some resources to back it up and make it happen. I mentioned the metering benefits at multiple levels in a business. Having alignment across the different business units can be achieved with cascading or interrelated KPIs. So you can see an example here where maintenance have got a focus on keeping leaks below a certain level. Engineering are responsible for designing and implementing the system, so they've got that KPI around the overall generation efficiency. But the sustainability manager, he's focused on finding those incremental gains and what can we improve so that it all rolls up towards a total corporate target. And having those KPIs in place just means that everyone's on the same page and moving in the same direction. It's also important to note that the KPIs are not just technical. As an engineer, that's what I always fall back to. But I've seen so many times where sustainability manager and it's got to work with multiple plants to get them all on the same page and achieve some corporate targets. But each site manager and each production manager is just focused on, no, it's production out the door, end of story. To get those lines of communication open and that cooperation, you really need KPIs in people's personal performance that are aligned, or at the very least have a degree of overlap. So it might be, production managers largely focused on production, but also has some environmental and cost reduction targets, which would then overlay with the sustainability manager. So that's a really effective way of getting that communication and cooperation happening. And finally, it always helps, and it's possibly one of the most important things, having an energy or a compressed air champion. And this person doesn't have to be the most technically minded or an expert on compressed air. In fact, it's quite often more beneficial to have someone who's able to influence others within the business and navigate through all those business processes and start to get people thinking about, well, hang on, let's take some proactive steps here for compressor replacement or compressor optimization, rather than waiting until something fails and then making a poor last minute decision. So I just want to pull that all together to give an example of what a compressed air strategy might look like. This is one that I'm working on at the moment. So this compressed air system, it's not the biggest in the world, but it's reasonable with a 30 kilowatt compressor, and it was observed to be approaching maximum capacity. There'd be times in the day where it was just running for 8 to 10 minutes flat stick. The site thought, well, look, we've got to do something with energy. A leak survey is always a good idea. So they did that, and discovered that 44% of the compressor was being consumed by leaks. So you might look at that and go, well, great, there's the answer. Fix the leaks. You've got capacity back in your compressor and, happy days. But when you dive into that further, there was a section of piping that goes underground to an old blending building. And there was a number of quite large leaks on the piping when it popped up in the other building. But that piping was between a wall and a new steel structure that was put in place. So unless you're about 15 centimeters in width, there was no way you're getting in there to fix those leaks. The compressed air load in the blending building was also very small. So a couple of pneumatic tools and a handful of pneumatic cylinders. So there was effectively a site champion here that was very keen to progress other options apart from, well, let's just bite the bullet and buy a 37 kilowatt compressor. So that way we've got spare capacity. Yeah, we'll use more energy, but we'll make sure it's a VSD. They were very keen on, well, hang on, are there some other solutions that we can look at here? So what we did was put metering and monitoring in place so we could actually track when the compressor is at peak loads and see if there's something on the plant that's really driving that, to start to narrow down with, okay, well, what are the big users? What's driving our compressed air consumption? Obviously, the leaks that were identified, the site undertook a leak repair process, but that takes time. And they've implemented an annual process to continue on with that for the moment. But then we looked at, well, that blending building, it really doesn't need compressed air. So we're working on converting the pneumatic hand tools over to electric, and the pneumatic cylinders over to an electric servo driven cylinder, which means that compressed air is not needed in that building at all. So way back at the isolation valve before it goes underground, the aim is to be able to isolate there, disconnect all that piping. Means that all the leaks that we can't actually access, and they are the biggest ones on the site, they've instantly been eliminated, and there is zero chance of them coming back. And likewise, because there's less pneumatics on the site, there's nothing in that old blending building now. Those leaks, any leaks there, they're never coming back. There's no compressed air. That's the easy way to fix it. So that this process should give us a good chunk of the compression capacity back in a short time frame, quicker than we could by going around and fixing all of the individual leaks on the rest of the plant. That's still an activity that needs to happen. And potentially, as this progresses and evolves, they'll have the spare capacity back, but then you'll have a load unload machine operating at part load. So there should be room for variable speed drive controls, and potentially fine-tuning pressure as well once the leaks and we've isolated some of the piping. So look, hopefully that gives you a bit of an understanding of why you might want to do a compressed air strategy, and some examples that that might hit home for something that you've seen on a site, or something that you need to deal with. But I'll hand back over to Jared now, and we'll get into some nitty-gritty of the technical detail on what can happen.
Thank you for that, Michael. And you've got one very smiling Alan Pearce, who, after we did a lot of assessments a few years ago, and really the conclusion is, I mean, compressed air is inefficient, so just get off it if you can. That should be the first thing you can do. And with so many new options to do that, it's really becoming viable. And when we looked at this 2 or 3 years ago, I think it was, Al, not many people were talking and thinking like this. So absolute music to our ears. And what we thought before we get to Edwin and go through some of these more technical solutions in a bit more detail, we thought it'd be worthwhile to have a little pause and just review those alternatives once more. So Alan, if I get you to come off mute, I'm going to take you through I'll run your presentation there, and let's go through some of these alternatives. Let me just share the screen, just one moment.
Well, while Jared's doing that, what I'm going to briefly cover is, in fact, what we found working with the New South Wales government on quite a substantial pilot project where over 100 sites were looked at, and there were 2 separate funding streams. One was to just do an audit. The other was to actually start doing some monitoring to get a better handle on things, and they were often both done at the same site. So this initial slide is just reflecting on some of the kinds of non-compressed air solutions that are around, and highlighting the fact that they can give very large savings, but also be much more flexible and more productive. So next slide, Joe. Thanks. Okay, so the New South Wales program, starting on the left there, was over 100 sites. It was pretty shocking, the extent of the problems we found. There wasn't much monitoring, and even when there was monitoring, it often wasn't very well used. A lot of the assessments weren't able to implement thorough monitoring. That's partly because they didn't access the second stream of funding, but anyway, that meant those assessments were of much less value, as I think Michael's highlighted the value of knowing what's going on. Again, Michael's already pointed out a really good example of a staged transition where you can identify parts of your plant that are a long way from the centre, or maybe need a different pressure, or work at different times from the main system. And these are all opportunities for transition in those areas to capture maximum benefit. One of the unfortunate things was that very few of the assessments we had done highlighted the multiple benefits that flow from doing something about compressed air. And again, Michael's pointed out that if you start engaging across the organisation and you start putting in data systems that can communicate with other data streams, you can start to really get productivity improvements. So across on the right there, this is just a quick summary of the sorts of findings. So your typical compressor system was up around 125 kilowatts with a couple of compressors. It was about 15% of total electricity use. And essentially, if you go down further, the losses were pretty big in terms of air leaks, and the cost-effective savings were pretty remarkable, comparing nearly $90,000 as a typical running cost and identifying $50,000 a year savings with about less than a year payback. You know, there's just so much low-hanging fruit, it wasn't funny. But again, just
Alan, that was 2020 prices. I'd suggest we could inflate all of those by, yeah, 25, 30% now. So big dollars.
Indeed, indeed. Yes, gee, the people who acted early would be laughing all the way to the bank, wouldn't they?
Absolutely.
Yeah, so I think really there are a lot of advantages to be had from not just improving compressed air use, but getting off it, as Jared said. Next slide. So we have got some. Oh, there it goes. So again, the thing that was a bit interesting to me was that the typical compressed air system, as we show there, was very inefficient. But essentially, people saw it as a sort of fourth utility, and it's just how you do stuff. Whereas once you start looking at the modern alternatives to compressed air systems, you've got faster, more precise, more flexible, more controllable. You've got more information, both from the system and that can be used by the system. So you can plan a lot better, as Michael's been talking about. So fundamentally, if you start moving away from compressed air traditional solutions into the alternatives that I'll show you in the next slide, you are opening up a whole new business model that can deliver you serious multiple benefits in productivity and managing your costs. Next slide. This is the last slide, and I'm not going to go through all of it, but I wrote a report which is on the A2EP website, where I went through all of the services that I could find that people were using compressed air for. So that's the left-hand column. And then I had a very tedious time searching through a whole lot of different supply chains and suppliers, and discovered that really there are lots of alternatives to almost everything that compressed air is used for. And they really all are a lot more efficient, and they really can transform your business success. And again, as Michael mentioned, and I stress, you don't have to do it all at once. You can develop a transition strategy. You can learn by doing, and you need to keep in mind too, and maybe Edwin will talk about this kind of thing, but some of the basic things, like say you fix a few of the obvious air leaks. If you're increasing the pressure of the rest of the system, you could be increasing the losses from the existing leaks that you haven't fixed. So, there's a whole lot of tricky things in these. And certainly there was a lot of scope for minimizing the inlet air temperature and the environmental conditions for the compressors, because they're less efficient if they're using hot air. So there's a whole lot of tricks. And essentially you can avoid most of them by just going off compressed air. I'll leave it at that.
Wonderful. Thanks, Alan. And I'll just comment on that. We had a line there, and you talk about digitalization. And I think it's been a few years since we looked at this, and we'd have a report on this sort of thing on Industry 4.0. But there is a dramatic improvement, increase of products available in IoT stuff that's easy to install on both monitoring the electrical consumption, flow, and temperature and pressure sensors now as well. So what used to be maybe a $10,000 exercise to get everything in place is far cheaper now. So definitely worth a look at some of these new solutions there for sure.
Yeah, I remember one of the suppliers was just introducing a generic electronic actuator, and they basically didn't need a skilled person to put in. And then they just selected from a range of about 50 apps to select the electronics and the data systems that they wanted. So, that's where things are going. As you say, it's becoming much more doable than it was.
Yeah, absolutely. Good one. Okay. Thank you, Alan. Much appreciated. Let's talk about solutions now and get into a bit of detail there. I'd like to welcome Edwin Burwood, the CEO of Energy and Carbon Solutions. Once again, a very experienced energy consultant and worked a lot in this industry for many years. One thing that's always struck me about Edwin is that whilst a lot of people may be talking about some new solutions and, gee, that would be good if we did this and did that, Edwin is out there doing it. So it is a great pleasure to have Edwin come in and share with us today some of the projects and things that he's been working on. Because this is really where the rubber hits the road is some of this work that Edwin's been doing. So Edwin, I'll get you to come off mute and take us through this presentation that I'll drive for you.
Am I off mute now?
Yep.
Thanks very much, Jared. Just following on from everything that Michael and Alan have said is absolutely correct. The whole change in the marketplace around compressed air is progressing forward, and the change in power price as well as ESG has certainly pushed compressed air forward, and I think it'll change a lot. Go to the next slide, Jared. So just an introduction to myself. I'm a chem eng. I've got a team of electrical, mechanical, and other chem engers that work with myself. I've been doing this now for 23 years, so it's a long time I've been looking at compressed air, and I was originally a graduate from BOC Gases. When I was there, I realised that 80% plus of the operating cost of an air splitter company was actually the electricity going into the air compressors. So this is where everything started from 23 years ago. Over the years, we've delivered over 800 compressed air surveys, whether it's flow, leak, surveys, all that sort of thing. And I've done over 300 air compressor projects in that time. Next slide, Jared. So the challenge with compressed air as an energy source, if we have an air compressor whereby we put 100 kilowatts in, we're essentially losing 85 kilowatts through heat of compression or heat and sound. So if I lose 85 kilowatts in heat back to the atmosphere or through a water stream to keep the compressor cool, and I lose about 5 kilowatts through sound, I end up with about 10 kilowatts of usable energy. So what we've got there is before we've even left the compressor, we've actually lost about almost up towards 90% of the input energy into the compressor and the compressed airstream. So unless we can change the law of physics and thermodynamics, there's nothing that can be done to address this in a normal compressed air system. And this loss of 90% generally happens before we even leave the air compressor. Next slide. Once we've actually got out of the air compressor, we may have something like, for example, a non-VSD machine. So we lose about 30% of that 10 kilowatts. So we lose another 3 kilowatts of energy. We have air leaks in the system. Let's say it's another 20%. And then we have mechanical losses. So the conversion of energy back to a piston or an air tool, we lose about another 30%. So we may put in 100 kilowatts of energy, but our round trip efficiency now is between 2 and 4% of that 100 kilowatts. Next slide, Jared. So the real question is, in a world focused on carbon emissions, is a 2 to 4% conversion rate of energy acceptable? In many facilities, the compressed air may be the largest motor in the plant. Sometimes it's 30% of the plant's energy usage, and therefore it's also 30% of the carbon emissions associated with electricity. Compressed air is around 10% of the electricity consumed in industry across the EU, China, US, and Malaysia. And so from an ESG reporting perspective or carbon reporting perspective, the air compressor is a significant contributor to the problems of industry today. So if we're actually losing most of that energy, or 80–90% of that energy into the compression, that's 10%, those losses, those thermodynamic losses, are actually about 8 to 9% of the world's carbon footprint being losses, which can be changed to new technology. Next slide. This is a case study that we actually delivered under the OEH program that Alan was talking about. We ended up doing about 16 projects under that one. And so we were approached by DB Sanders Salo under that program to evaluate some 16-year-old Champion 37 kilowatt compressors. They're running 24 hours a day, 7 days per week. And what we found through monitoring, is that we were using about 32.1 kilowatts as an average, and it was over 30% of the site's total energy consumption. The site did need compressed air for 2 critical CNC machines, but they were also using a lot of the compressed air for air tooling and blowing off processes with handguns and things like that. So They were essentially leaving these compressors running 24 hours a day, and they never ever turned them off just in case they actually needed compressed air for a process. The ultrasonic leak survey of the facility found that the old piping had significant air leaks, losses and holes in the copper piping, which dated back 40 years. So we have a significant loss and a significant carbon footprint here. Next slide, please. Okay, so what did we do? So the energy and flow metering indicated, as Michael suggested, we had significant system losses. We had poor system control. We had load unload on a very inefficient 16-year-old compressor. The compressors were running 24 hours, 7 days a week, just in case they're required. And the compressed air was used mostly in tooling. However, we did have a critical use, which was 2 multi-million-dollar CNC machines that required compressed air when they ran for 2 or 3 days straight. So what did we do? We took a system redesign and we converted all the pneumatic tooling on site to the latest technology and matched to Milwaukee battery tooling. And we torque matched all the equipment so that essentially we had no loss in productivity on site. And what we did was change that across. We resized the compressors from 37 kilowatt machines to 15 kilowatt VSD direct drive machines. And we selected a machine with a 10-year warranty for the client. And we replaced the 40-year-old piping with a leak-free stainless steel compression fitting right around the facility. There was 340 meters of new piping went in on that. And so what we ended up with, once we pressure tested it, we had less than a 0.1% loss rate once we put all the new compressed air piping in. Next slide, please. So what we found at the end of the results, and there's the monitoring on the right-hand side, we actually ended up with an average energy consumption going from 31.7 kilowatts to 7.2 kilowatts on average, which was 77% when we're actually running. And we utilized a lot of the government programs to work with this one. So the total project value was around 124,000, including all new, 2 new compressors, duty standby, dryers, filters, setting up the system, flow meters, power meters, and the 300 meters of piping. We asked and were granted for the audit on this one originally. And we then went to the New South Wales Manufacturing Efficiency Fund, where they funded, because of the air audit, we got $54,000 back on that program. The actual investment was $62,000 by the client, but we delivered 139 megawatts of savings, and this was in 2020. So we got about just under $16,000 a year of savings. Simple payback was 3.9 years. And you can see here on the right-hand side, this was the daily energy consumption for the compressors essentially before and after, once we flattened out. And we had the compressors on an automatic rotation, so they turned off of a weekend, which is why it's much lower. So in total, once we actually switched the machines off of a weekend and only brought them on as required, it was about a 92% energy saving. So much more efficient. And for this client, we ended up, they were that impressed with it. This program actually went global for this group. They've got 30 plants around the world. This program, with the solar we rolled out with this and the lighting program, we pulled their site energy consumption down by more than 52%, which is the carbon footprint. And then they rolled this around all their European, American, and South African sites. So that was one of the success stories that came out of that New South Wales OEH program. Next slide, please. So a lot of plants, you can't actually reduce the energy consumption. And this is another example where you can be a little bit smart about things. So this is a plant done back in about 2013. The plant had a 160 kilowatt oil-free machine, had a lot of VSD, air end, and reliability issues because it's done over 120,000 hours. It was tripping continuously. It was 4 hours out of Sydney, and they had no backup. So we had a lot of reliability and downtime issues. So there was no backup on site. Cost of ownership, as it's the end of life. And the process required large volumes of compressed air for manufacturing equipment with minimal opportunity to change the technology. So not quite the same as what we had on the other plant. We couldn't do a lot with it. However, what we found through an audit of the site was that the aluminium cans were washed down with warm water at 70 degrees to remove any aluminium carryover. And that process used 160 kilowatts of heating elements continuously on a warm single pass of water And so that process was costing close to $100,000 a year just to heat the water. Next slide, please. So what we actually did, we couldn't actually remove any of the demand for compressed air on that site because of the way that the plant ran. So instead what we did is we redesigned it with a heat recovery loop, and we produced 40 litres of water a minute at 70 degrees for the plant. The electrical savings, we reduced the consumption on site by turning off the 120 kilowatt heater. So therefore they could preheat, and you can see the piping on the right-hand side there. And what we end up doing with the M&V on this one, we had a 929 megawatt hour saving from both the compressors as well as the electrical heater, 845 tonnes per annum of carbon, and we reduced the whole site's multi-million-dollar electricity bill by 10% on this one. That was the M&V reported back to Oz Industry. Next slide, please, Jared. So what we found on this one, we ended up with a $123,000 grant. You can see here through the redesign, we've actually got 3 Ingersoll Rands here in a row, 1 VSD, 2 base loads. So we also got, in addition to the $123,000 CTIP program, we got some ESCIs on that for 47 grand. So the total funding was more than 70% of the project, and the payback was less than 2 years. The plant improvements, well, we had 10% reduction in plant carbon footprint, significant reduction in plant downtime because we had duty standby on site, significant reductions in maintenance costs because the 160 kilowatt VSD didn't need new motor, didn't need new VSD, and didn't need new air end, and the savings were greater than $120,000 a year per annum. So, and with the 2+1 design that we've got here, the 3 Ingersoll Rands, we could run the plant on 2 out of any of the 3 machines. So, and they all had heat recovery, so that didn't affect that process. Next slide, please. So the conclusion is that compressed air is fairly much the most inefficient process in your facility, yet likely to add one of the largest sources of carbon emissions and energy costs to the plant. Considering these changes, there's a lot that can be done. So things like swapping out the air tools for battery powered tools, that technology has come a long way in the last 5 years, whereby you can now get the sort of torque rating out of a lithium-ion battery we couldn't get 10 years ago. Changing technologies, considering things like PLCs and stepper motors, as Michael and Alan spoke about, addressing compressed air leaks and monitoring and measuring that, and I agree completely with Michael on that, on the actual continual monitoring of those systems, which we do these days. And if you can't change the process, what can you do with that 80% plus of the input energy to reutilize it for other uses on site, like that heat recovery of flashing bottles, of washing the bottles out, or where else can you actually use that low-grade heat so that it's actually utilized rather than just venting it out of the aftercooler back to the atmosphere? So plenty of opportunity there. There are just a couple of case studies of things that can be done. But my view on this is that with a 2 to 4% conversion rate, compressed air is going to be one of the big areas that industry needs to target over the next 5 to 10 years to meet the ESG targets. Thank you, Jared.
Edwin, that was absolutely fantastic. Thank you very much for those cases, and you've really showing what's possible there. That's great. And I'm sorry, but I feel like I've got to bask in some of this data sometimes. I've got to go back to that graph and just look at that dramatic change and show really what is possible. And I say, if that metering wasn't in place, would there have been pats on the back? Would there have been celebrations and happiness? You know, that just once again it reinforces what Michael started with, that need for the metering there. So thank you so much.
Absolutely. This is one of the case studies that was used by OEH to send to Canberra around compressed air.
Yep. And
that metering was actually done, this initial stage was done with the Symbol loggers, and Symbol is obviously a member of A2EP.
Brilliant.
Yeah. Can I just cut in and say, Edwin, you're making me look quite conservative here.
Could have gone for more, Alan.
Nice change.
And if you do have some questions, please pop that in the Q&A. We've got a couple there, and I'll read them out. And Michael's already answered them, but please pop them in the Q&A. We've got 5 or 10 minutes left, so we've got time to look at them, which is great. Edwin, just want to check something there. You said you're producing 70-degree hot water from the heat recovery.
Yep.
Was that recovering from the oil or from the air that being discharged? And maybe you could take us a little bit more through that setup and how that was done.
Yeah, certainly. So when we specified the machine, so when you put a heat recovery into an air compressor, like a screw compressor like that, it's done on the oil circuit. So we bought those machines because we needed to upgrade the machines. We specified them as part of the package when we bought them. And so what happens is most of the heat load is actually coming out of the oil. So very little of the heat load comes out of the actual hot air. It's actually the recirculating oil loop. So the heat exchanger in those goes between the air end and the aftercooler.
Okay.
So it's basically on the hot water side, on the hot oil side.
And 70 degrees. I just came off a meeting yesterday. Someone tell me the most you can get from the recovery is maybe 40 or 50. Does it matter the type of compressor? Maybe that was an oil-free compressor.
Yeah, it certainly does. Particularly if you have a water-cooled machine, you're going to get a lot less. Depends on the type of machine. You can't do it with, for example, a centrifugal compressor or an oil-free screw. But if you've got lubricated screw compressors like this, where you've got that oil recirculation system within it, absolutely, we can push to about 75 degrees. That's about as high as you're going to get, and it depends on brand and setup and all sorts of things like that.
Excellent. So that's oil screw compressor, 70 degrees. Good.
Yeah, I think one of the other interesting things is this ties in with the emergence of higher temperature heat pumps that could take that even 40 or 50 degrees, but 70-degree heat and really crunch it up to quite a high temperature at high efficiency to replace some steam even.
Yeah,
absolutely.
Absolutely. Yeah.
There's certainly heat pumps available now in Australia. It's 110, 120 degrees. So, but you need the heat source. If you try and create 120 degrees with only 20-degree ambient air, that's not going to be efficient. So, yeah, well, that's an absolute game changer. Michael, we had a question there, which I thought would be interesting. We'll just read that out and make sure we're clear on that one. You're asked about why did you have the temperature sensor in that recommended setup? I just wonder if you could talk us through that answer there.
Yeah, sure thing, Jared. So my preferred method of measuring compressed air is with a thermal mass flow meter. And the way that device works is it basically has 2 very small temperature sensors in it. One's heated and the other one is slightly downstream. So the more air that passes over that heated element, the more temperature carries over to the next sensor. So by the nature of that type of measurement device, it has a temperature component to it. The temperature of the compressed air is also relevant to making sure you've got accurate results. So you end up using temperature and pressure to normalize those results. So, it's a lot more obvious with pressure. For example, if you measured the flow in a pipe and it was at atmospheric conditions, that's going to be a very different flow to if it was at 7 or 8 bar, like a compressed air system. So it's a seventh of the volume within that pipe. So you've got to adjust for what pressure it's at. These meters do pressure and temperature correction, so you've got accurate readings.
Brilliant. Thanks, Michael. And while we've got you there was another question there regarding that the blending building that was had the high leaking underground pipe on the way there, and the question being, why were they using compressed air tools? Was it a fire risk, or was it the tool size, electrical safety? Why was that?
And I think this comes back to a lot of things that are compressed air related. Convenience, and that's just how things were done. They moved a small maintenance workshop up into the back part of that building, and along with it went a spare air receiver that they had, and the guys went, well, we'll just connect our air tools to it and we'll use those. They use them once a week, once a fortnight. So very infrequently. And because they weren't doing any high torque applications, it was quite easy to convert over to electric. They didn't need anything specific. And more importantly, those two maintenance guys, one of the hardest things is the behavioral component to overcome. If you say, right, I'm going to take away your compressed air driven pneumatic tool that gives you a nice cooling effect as the air comes out, and give you a lithium ion, not always accepted as well. But because this was just a convenience thing, there was no real application that needed, high torque or specific. They weren't using the tools for 8 hours a day.
That's what happens when you don't have the data.
Yeah, this comes back to the language that people were using about compressed air as the fourth utility. Oh, we can just plug stuff in.
Easy to use, easy to lose. Yeah, that's the one. Question, I think, for Edwin there is, how did the customer deal with the change of air quality going from oil-free to oil-flooded screw compressors? Was that an issue there? I think that was maybe for you, Edwin.
Yeah, no, it wasn't an issue on that one. What we did was we put in an oil-free pack on that one. So the application wasn't actually food grade on that requirement. So we determined that the requirement wasn't required. That had that as an internal standard globally beforehand, before the company was sold. And so when we actually looked at it, we did an oil-free pack with activated carbon towels and all that as part of that project to make sure we had technically oil-free air, but the cost of operation was significantly less and the capital cost was less for what they needed.
Gotcha, thank you. And then you mentioned about monitoring electricity and flow, but not pressure. Is that the case?
Most flow meters these days have pressure transducers in them as well. When we did this like 10 years ago, we didn't really have that option to integrate in cost effectively. So these days, most flow meters we get actually got pressure in them as well. So that first one with DB Sander Salo, we did change the pressure set points on that one as well. And that's one of the reasons the power came down as well. So we could control it much better.
Gotcha, thank you. And a question here about the compressor drawing consistent currents in a load, unload respectively, and a relatively consistent operating cycle. How critical would you say implementing kilowatt metering is if the duty cycle of the compressor can be monitored using the discharge pressure and airflow?
Yeah, look, I might jump in on that one, Jared. I think this comes down to your objective and largely your accuracy. So you'll see quite a variation in the supply voltage to a site. So with just CTs to know what your currents are, loaded and unloaded, that's good. It's a good start, but you won't pick up the true power costs because you're going to have 15 to 16% variation in the voltage being supplied, and that impacts your total kilowatts consumed, which is what you're paying for on your bill. The other big part of an electricity bill, which is 30 to 40% of it, is demand charges. So the power factor of the motor will vary between loaded and unloaded. So if you are really trying to drill down on your demand charges on your bill and on your site, then you probably want to have proper power meters available to help you drill down and understand where is, maybe I've got poor power factor at certain times. That's probably when your compressors are unloaded. So it really comes down to your objective. Definitely flow and pressure measurement gives you a huge amount of information. If you then want to be able to say with some certainty what your efficiency of generation of that compressed air is, you do need the power meters. But again, it comes down to objective and accuracy.
Excellent. Thank you.
Sorry, absolutely. The what we could get away with 15, 20 years ago in terms of just measuring amps doesn't fit these days because the cost of metering is so low. So if you want anything accurate these days, you've got to put real energy meters in to be able to get that proper data. As Michael said, it's all about power factor, load, and voltage, and the technology these days allows that very cost effectively.
And I'm sure you've seen it as well, Edwin, where if you've got a power meter on there, you can actually see, the individual phases. You can start to see some phase imbalance, and and you can get some early warnings of compressor failures that way as well.
Absolutely, absolutely.
Good one. Thank you for that. I'll try and get through this slightly long question here, but we've got someone here with 160 kilowatts of compressed air at a fashion manufacturing company, and they're running 2 shifts, 2 8-hour shifts, and they've been told just to potentially just run one compressor only for the 16 hours and remove the other compressor. But they're not sort of sure and convinced that's the way to go, or should they be running one and then the other? And I'd suggest that's not a simple answer we could probably get to with that sort of information, and depends on the different types of the compressors and whether or not they're identical. But just wondering if Michael or Edwin had an opinion on that question there.
I think it comes down to there's a lot of variables in there. So what sort of flow? Are they the same? Are they variable speed? Yeah. What's the actual use on site? There's a lot of variables in there. It's very hard. But the second case study I put up was a 160 there, a single 160 that changed to 375s, which was the most cost-effective way to build that plant. But it depends on a lot of things, like what sort of compressors are the 160s and that sort of thing. So.
Yeah, exactly. So a little bit more info would need on that one, but good to ask the question. Thank you for that one. Final question. I'm not sure, Edwin, you're going to have it at your fingertips, but do you recall what the water flow rate through was the oil heat reclaim heat exchanger? I think I saw 40 litres per minute there.
Yeah, so each one at that sort of temperature. So the return temperature, we could do a 15 to 70 degree rise on those ones. I think it was around, and this is 2013, it was about 20 litres or a bucket load per minute per machine.
Gotcha.
So,
perfect, thank you. Before I do a bit of a wrap up, Michael, final thoughts. You gave us some gold there to work with. What's your final thoughts in sort of 30 seconds there?
Oh, look, I don't want to sound like I'm harping on about it, but having the metering in place, that example that you were just sort of talking about with 2 compressors versus 1 compressor for the shift and the amount of variables that are there. If you've got metered data, you might be able to instantly see, okay, yeah, this machine is more efficient than this one, even though they're identical, because it's the quality of the overhaul at some point, was different. You can then preferentially use machines that way, but without the visibility, without the transparency, you're taking a guess. You can be educated guesses, but you're still guessing at the end of the day. And as Edwin said, the cost of metering, it's come down. So there's fewer and fewer excuses.
On to do it, and lots of other tips there with getting a compressed air champion. This is not just about technical solutions; it's behavioural. So fantastic. And then Edwin, to you, any final thoughts or final recommendations?
I think that compressed air is going to become the forefront of following the whole heat pump thing. I think it's probably the next area that the people will start looking at, because of that whole thing around the 100 kilowatts per 100 kilowatts we put in the round cycle efficiency is like 2 to 4%. So as people become aware of that, I think that compressed air will certainly become more of an area of focus over the next 5 to 10 years, and we'll see smaller and smaller compressors as things like we've just demonstrated become more the norm rather than the extraordinary.
Absolutely, and I note that you've freed up for one site 30 kilowatts and another site around 100 kilowatts, and with sites needing to electrify more, yes, whether that be for mobility or for heating, they're going to need that electricity, and you've freed that up for them.
Yeah, it's the ESG reporting, it's the carbon reporting of the ASX listed, it's the net zero for the big industry. This all adds carbon footprint, and if you can start taking 90% out of a process, that's a big impact on carbon footprint of reporting.
Yeah. Brilliant, well done. Thank you to you both. Alan, look, I'm happy with this. It's great to see the progress over the last a year or two. What's happening here? Any final thoughts from yourself?
Yeah, well, again, I think people should also be looking at the processes and the need for energy, whether it's heat or motion. And so there's a lot of opportunity to really revolutionize your business model And again, that's where, you know, A2EP's got the word productivity in it, because we don't just look at saving money on your energy bills. This is about transforming your business for the 21st century.
Brilliant. Thank you so much, Al. And so if I just do a quick wrap up and let you know what else is coming up for A2EP, plenty going on. So on the 20th of this month, we've got a webinar on mechanical vapor recompression technology update. And for the picture behind me, you'll hear a little bit more about that project and what's happening there. On the 27th this month, we've got an update on what we're doing with renewable heating programs. There's so much research underway, and we're really keen to share with you what's going on there and what's happening, and see if you'd like to get involved in that research. And finally, Thursday, the 12th of October, we're going to have our second heat pump site tour starting in the Sydney CBD, and having a look at a couple of sites there before we move out to the TUI site at Lidcombe. And when we go there, you will see virtually every decarbonisation and energy productivity tool in use, from biogas to metering to mechanical vapor recompressors. It's all there, so it's going to be a fantastic site visit, and you'll be able to book now on our website for those. If you do want more A2EP, follow us on LinkedIn. Just type in A2EP and hit that follow button, and you'll see you'll be up to date with all our news and posts, and feel free to register for our e-news at our website as well. So all that's left is for me to give another thank you to our presenters today, Edwin and Michael, and of course Alan, for joining us. Thank you so much for your presentations. Thank you to those joining in. And if you've got some more questions, absolutely feel free to reach out to me, and I'll make sure you do get connected with our presenters today. But thank you for joining us, and wish you a very pleasant afternoon.